All right. So as I said, like for more or less the final, the summary talk of this seminar, I wanted to kind of bring up. Well, the title here is very general, right? Is music complex? In what sense? So what I mean by this is there is this complexity theory, right? And I think you mentioned this before, that might apply to the idea of emergence of musical structures through the process of generative mechanisms, because we talked a lot about the generative mechanisms, right, and how we can learn them. So kind of the motivation really is that we discussed the adaptive process of acquiring a generative representation of the world, or in some sense, the music, which was kind of the data, the musical data, or other musical experiences for us are kind of the external world. And it's learned through some process of inference, where by inference we meant, well, we create some kind of a internal representation of the world that helps us predict or understand or categorize the world. And in this adaptive process of trying to uh, basically minimize the surprise or the error, that was kind of the whole free energy principle of learning. And this learning was also presented as homeostasis between the organism or the learning system and the surrounding world. So it's a very particular approach. And frankly, it doesn't say much more than actually how you could learn something about the world in order to coexist. Right? And the surprisal, in some sense, a measure of your success in understanding the world. So from this, we took some other ideas of, of course, that the Bayesian brain and the predictive coding were part of this scheme. But then the whole idea of hallucinations and the idea that the system would basically imagine things and compare this to the stimuli were all part of this whole framework. Um, so kind of the phantom limb effect, right? Or tinnitus was part of this. And of course, the virtual reality and the dreaming. So the whole notion was that the system not just learns to classify or answer specific questions, but actually builds a representation of the outside world. Um, and for that purpose, the representation bears a lot of relations to language. And music is not exactly language, but at least for the purpose of today's discussion, language can be considered as a system for representation. And language will be usually used to communicate between different subjects, right? You can think about language as something that communicates a speaker to a listener. But kind of the idea that it uses the representation of the world in some symbolic way. So if language is a system for representation of the that communicates symbolic information. So there's a that here. Okay. Language can be considered as a system for representation that communicates symbolic information about the outside world. And we kind of a little bit mentioned the idea that there is an aspect of communication or prediction over time. We try to formulate the information rate as some kind of communication system, but that was really in a sense of expectations as some kind of a communication over time, but there is no really aspect of communication between listener and the creator, or between multiple musicians. But still, let's stay for a moment with the idea of the language, and then there is this question that some of the complex system theory tries to answer, is looking at the structure of natural language. So are there special structures of natural language that distinguish it from artificial? And does complex system theory apply to music? So what I mean by this is really some very specific aspect of statistics of text and other phenomena that I don't know if any of you have already encountered this concept, but there is this Zipf Law, and it was a linguist, but I think his first work, or at least a lot of his initial work, was done just investigating other natural phenomena like sizes of cities. But most commonly, or the most famous result, is about text or natural languages that exhibit very particular statistics. It also resembles something else which is called 1 over f noise. So I have to define what it is. So we'll see in a second what the Zipf's law is. But in some sense, what it shows is that there is some kind of a non-trivial or very particular way that words in the language, or sizes of cities, or even the wealth of people, basic distribution of money in a society are related. So if you want to rank things according to their statistics, they seem to appear in very particular ways. And then the next question was, well, why this happens? So there were many possible mechanisms were proposed, and one of them is preferential attachment. So I'll talk about what it is. Actually, we have a video. I kind of, I think, posted this video also on Discord, but I will go through this video today. So then the question is, if there's something strange about these statistics, so what is the mechanism that creates them? And one of the common models is Herbert Simon's model for text, where he claimed that that specific statistics that happens is because as text is being written, more and more context emerges. So the model, the basic mechanism, before we describe what the statistics look like if you follow this mechanism. But if you can just think about this as a way of generating data, and so you choose a word, you basically keep adding words. So you have a big vocabulary, and you can choose words at random. But the idea is that once you choose a word, the next word, in some sense, has a choice between being a new word or repetition of an existing word. So there is this tendency of reappearance or recopying or replication of existing words. So in this text here, it says, as the context emerges. Context means more and more text is generated. There is a tendency to recopy. It favors the appearance of words that have already appeared and inhibits the use of new words. And by having this type of behavior, it creates very particular structures, and some people kind of can also look at this or describe this as some way of kind of a growing a structure, growing a graph, and having these kind of different scales of looking into this phenomena. And this is sometimes called scale free, and we'll see why. And the last thing I'll try to do is to try to see this in the context of this information theory that we were looking before, and see if something like a least effort, or the communication process, least effort in communication between a listener and a speaker and a listener also results. So this kind of two different attempts to describe this Zipf phenomena. So maybe first we need to kind of look a little bit into this peculiar phenomena. So let me play this video. It's a little bit long, so let's see if we go through all of it or skip some parts, but at least the introduction kind of starts interesting. Okay, I don't have the sound. No, no. Can you hear this?
The is the most used word in the English language. About 1 out of every 16 words we encounter on a daily basis is the. The top 20 most common English words in order are the of and to, a in is I, that it for you was with on, as have, but be they. That's a fun fact, a piece of trivia, but it's also more. You see, whether the most commonly used words are ranked across an entire language or in just one book or article, almost every time a bizarre pattern emerges. The second most used word will appear about half as often as the most used. The third, 1/3 as often. The fourth, 1/4 as often. The fifth, 1/5 as often. The sixth, 1/6 as often, and so on, all the way down. Seriously. For some reason, the amount of times a word is used is just proportional to 1 over its rank. Word frequency and ranking on a log-log graph follow a nice straight line, a power law. This phenomenon is called Zifs Law. And it doesn't only apply to English. It also applies to other languages like, well, all of them. Even ancient languages we haven't been able to translate yet. And here's the thing, we have no idea why. It's surprising that something as complex as reality should be conveyed by something as creative as language in such a predictable way. How predictable? Well, watch this. According to wordcount.org, which ranks words as found in the British National Corpus, sauce is the 5,555th most common English word. Now, here is a list of how many times every word on Wikipedia and in the entire Gutenberg corpus of tens of thousands of public domain books shows up. The most used word, the, shows up about 181 million times. Knowing these two things, we can estimate that the word sauce should appear about 30,000 times on Wikipedia and Gutenberg combined. And it pretty much does. What gives? The world is chaotic. Things are distributed in myriads of ways, not just power laws, and language is personal, intentional, idiosyncratic. What about the world and ourselves could cause such complex activities and behaviors to follow such a basic rule? We literally don't know. More than a century of research has yet to close the case. Moreover, Zifs Law doesn't just mysteriously describe word use. It's also found in city populations, solar flare intensities, protein sequences and immune receptors, the amount of traffic websites get, earthquake magnitudes, the number of times academic papers are cited, last names, the firing patterns of neural networks, ingredients used in cookbooks, the number of phone calls people receive, the diameter of moon craters, the number of people that die in wars, the popularity of opening chess moves, even the rate at which we forget.
Okay.
There are plenty of theories.
I will stop for now because we'll talk about some of the theories. It's a fun. We'll see if time allows. You can go back to this video. Of course, it's not perfectly straight line. You know, there are these deviations at top, which might be pretty important. And there's like some of the more recent research actually tries to address the idea that there is some kind of emergence of heavy top here. But I mean, there's definitely this trend that there is this kind of a middle class that has a very particular ranking. So the size is inversely proportional to the rank. So then the question is, I mean, what does it tell us about music? So if we look at, people trying to look for Zipf's law in music, there was also a paper. There are several, but I mean, like one that I refer to here from 2005 in Computer Music Journal that tries to analyze these different slopes. And the claim is that the natural slopes are very much around -1, while things which are random or white noise or pink noise are much flatter. So there is less of that kind of critical -1 slope. And in some sense, 12-tone music is much closer in terms of its ability to create these different rankings. So if we start aggregating things into units and counting which is the one that replicates a lot and which one replicates less and less, in some sense, 12-tone music tends not to be aggregated into structures, or at least the statistics in 12-tone music are closer to something which would be like pink noise. Pink noise would be basically noise with some filtering, some correlations, but it still doesn't create these hierarchies, while different styles do. Maybe in some sense, if -1 is ideal, and jazz seems to be there, but I mean, there is not much of a, I mean, this article does claim that there is some relation between aesthetic perception and Zifs Law, but I don't really want to go into that specific question. But overall phenomena is that frequency of occurrence of some musical element, in this case, this example is melodic intervals in particular piece, do have a large chunk of these intervals distributed according to these proportions. So there is more and more evidence that music actually is created this way. And then there is also this inverse approach is, can we take a mechanism, can we take some, rather than instead of taking a Markov process or taking some other probabilistic model, do we create some dynamical system, create some kind of a set of evolutions of elements that will recreate this law, and we use them for composition, because in some sense maybe they will be more interesting, maybe they'll have more hierarchies and better relations between very often repeated elements and rare elements that for us maybe is more natural. So so the basic model that we mentioned, the Simon's model for language, actually proposes a very specific mechanism, which he calls this preferential attachment, or the rich get richer. And what it means is that you assume you have a vocabulary, and then you have some kind of a innovation probability. Okay. So with probability rho, whatever that symbol is, rho, the next word, you choose a word that has not previously appeared. So basically, you pull from the vocabulary, from the dictionary, a new word. Okay. And with 1 minus that, you choose one word from all the words that have come before and reuse this word. So if you think about this as novelty, so innovation, mutation, this will be replication or imitation. So here's kind of the idea of this process. Let's say you have 21 words, next word, okay, is new with probability rho. That's what it is, okay? So we start with that, and then let's say you have another word, you can choose maybe and then of course you have a probability of choosing the or and in the same way, but you choose the again, so it starts being 2 to 1. Maybe you choose ook, and then you have a probability to choose new word, maybe penguin, or if you don't choose a new word, you look at these three, so you had maybe 2 to 1, so you will probably keep growing one of these, you had another there, and then you play the game again. So I hope the mechanism is pretty clear. Basically, you either bring in a new element, or if you decide that you don't want to be new, you go and you say, I will choose from the existing ones. And within the existing ones, you basically, you can think about this as choosing equally from all the appearances, or you can group them in groups and then say you choose proportional to the size of the group. So this way, the bigger groups, as the mechanism keeps evolving and these groups emerge and become bigger and bigger, the bigger is the group, the more attractive it will be. So what you keep constant is just this probability for mutation. But the introduction, there is constant introduction of novelty. But if you don't choose to innovate, you go into the replication regime, And in that replication, you will replicate according to the existing structures. And then the bigger structures will basically attract more. This is why it's also called sometimes preferential attachment. You can either detach yourself, or if you attach yourself, you have a preference which is proportional to the size of the group. So if there are any questions, but if not, then let's look at what structures emerged. Actually, there is a very nice simulation of how things emerge using this model. So let me switch there. Okay. Now this is kind of abstract, right? We don't tell at this point anything about what these elements are. They're just points that are going to be appearing in the simulation. I hope we can see this on the graph. Yeah, I'll scroll up and down. So if we start with some kind of not a very small, but like a reasonable probability, I don't know, 1.4, which means, or let's go like 1.5, which maybe is a little high, but still, with 50% chance you will introduce a new point, and with 50% you will just join an existing group. Okay. And yeah, so let's see how it grows. Okay. So here we go. And this is the slope. I mean, they're basically ranked by amounts of repetitions. So in this process, we can see that there is one large group. So this specific paper actually focuses on the first mover advantage. So the fact that this one point is much bigger than the rest. But you can see that the other points tend to be distributed along some kind of a line. If we try to do this with, maybe let me stop this and change to slightly lower probability. Here you have a few more groups appearing. I mean, there's still a large group, and it kind of starts aligning itself in a maybe more interesting way. And you can think about what are the proportions that are needed. So this one is actually creating this ideal -1 slope here. If this is that Zipf slope here, and you can see that the emergence of these patterns. So you have maybe few dominating groups, and then the rest are kind of fillers. If we go to very small innovation, you'll basically get 1 or 2 big groups, and the rest become very small. Okay. If we even go to an extreme, you'll basically have pretty much one group and bunch of things that just attach to it. But there's this huge gap between one large idea and the rest are just little kind of tail here. Okay. The other effect is the opposite. Like if we put a very large innovation, which in some sense means that no idea wants to join any other idea. You can think about this as distrust or something that nobody wants to join anybody else for whatever reason. Okay, what we get is pretty much equal distribution. Let me see why. Yeah. See, all of the points are new. Nothing is being aggregated. At a certain point, it might start aggregating, but really very small chance for that. Yeah, so suddenly you have few of them that attracted other points. But basically, you kind of have this structure that you might have few points on top and pretty much equally distributed tail with a big drop. So for some reason, it seems that a lot of the natural processes, at least with this specific simulation, which is like somebody else taking Simon's model and slightly amended or changed for the purpose of demonstrating that first mover idea. But this is the Simon's model. This is basically kind of the attraction. So as we showed, like somewhere around 0.1, you get pretty nice behavior, even if you do get maybe slightly heavy top. Okay, so you have maybe one big cluster, some of them which are secondary, and then a lot of them start getting organized along this slope. So why this is relevant at all? Or let's maybe go back to our slides and see, and just to make sure everybody could see the simulation, right? I mean, because I was switching screens, right? Good. So there are some other, actually, I think I did link here to a video. I mean, the same question or phenomena of distribution of something, ranking, and also applies to distribution of wealth. So just maybe to show how broad this idea is, I don't know if I've linked this video. Let me see if I did. It should be pretty short. But this idea of like wealth distribution, how it builds up. So the idea of preferential attachment in some sense is sometimes called, richer get richer, right? So the more you have, the more money you attract, right? So is this a link? Probably it's not. Okay, but you can imagine that these models also are of interest to economists and others. So one of the questions I want to kind of to bring today is this process, even if Zifs Law is, can be demonstrated in music by, of course, you have to define what are your units, what are you measuring, and then start enumerating and calculating the frequencies of appearance. At least the preferential attachment model is a dynamic model. It's a specific way of suggesting that once you start generating things, there is this another layer of dynamics that happens, which actually now creates these preferences or biases. So whatever you started generating will be more influential than before. And this is not something that really the free energy, at least the way it was formulated so far, can explain. The free energy just tells you that you keep generating, right? And it doesn't tell you anything about the fact that maybe what you generated now becomes more important, or it becomes the context that now limits your possibilities of generating something new. So I want to kind of a little bit discuss this idea. Okay, so in its simplest form, Simon's model postulates that during the process of text generation, new words are added at a constant rate. So there is kind of a novelty rate always, while a word that has already appeared is used again with a frequency proportional to the number of its previous occurrences. So that kind of creates this basic split between novelty and imitation. Now, the creation of context in language is intimately related, and just to be kind of give you for disclosure, I mean, these are all excerpts from this paper. Okay, if you want to find it. The paper, I think the paper was actually 2004, but for some reason on the PDF itself, Damien put 2008, so maybe it's an updated version. The second point was the creation of context in language is intimately related to the semantic contents of words, yet to their meaning. So this is from his paper, because he was kind of referring to language primarily, and he has other papers that deal with language. So he kind of tries to see or explain the idea of this dynamics of text, the preferential attachment, as related to meaning. And in that sense, semantics is in fact essential to the function of language as a communication system. So this was kind of that basic premise, is that they attach words attached to other words, because once you started talking about some subject, of course, there are a lot of filler words like the and so on that are required all over the place. And that maybe has its own semantic category, it's pointing to something or given our article. And then, once you also define what are your categories, what are you talking about, then other words that related to the same will be more attracted to that meaning. So even though semantics is not necessarily, identifiable in this preferential attachment model, at least that kind of makes sense that words will cluster according to like groups of related meanings, and then and in that sense this also explains language, because if language is a communication about some topics, once you choose the topic, the words will be and the more and more you develop the topic, the more words will be basically joining, or you will be replicating words according to the topic that you talk about, and you will not be changing your topic every time. So semantics in the strict sense can be defined as a connection between symbols and entities that they represent in some extra symbolic world. And this is true for language. Now, in music, generally the musical message doesn't convey information about an extra musical world per se, right? I mean, you could, in some senses, in some cases, find more direct relations to something outside of the world functional music, but in general, it's kind of very abstract. So what he says about music is that, the conventional correspondence between musical elements and non-musical objects or concepts, a dictionary seems irrelevant to its cognitive functions. So there is this basic question. I mean, if at least in language, the preferential attachment model seem to be motivated by the fact that words have specific meanings, and this is why they will be sticking together, why in music you will have musical elements sticking together. What he claims is the notion of context is essential to both language and music. In the two cases, context can be defined as the global property of a structured message that sustains its coherence, or in other words, its intelligibility. So again, he didn't really define what coherence means. He didn't define in this paper what intelligibility means, but he kind of tried to justify the existence of Zifs Law in this paper. He also does provide some examples, data examples of music that he analyzes that shows this behavior. And his hypothesis or proposal was that, context actually doesn't have to have meaning. I mean, context carries its own meaning with it. This approach, in some sense, assumes this growing model. But I want to also talk about a different idea, which in some sense relate to some of the predictive information. In some sense, it's not exactly predictive information in a model, but it uses the ideas of communication channel also to explain. So this is a different model that actually looks not so much at the growth, at the attachment process, but at the communication properties of a message. Okay, this is a different work that actually assumes that there is a speaker and a listener, and there is an information transfer between speaker and listener. So in that sense, it's kind of reminds that information dynamics idea. It assumes that you have signals that kind of represent or are supposed to be related to references. Now, in this case, the references, at least in language, are supposed to be these semantics. What it will be in music will be part of the questions I wanted to address today. Maybe these are the latent variables. I mean, the references are not exactly we don't really know what they are. Maybe they're emotions, right? Maybe there are some structures that conventions of style built for us. But at least for the purpose of this slide, let's think about this as language. So you have words and you have the meaning of the words or signals, and then the physical references to identifiable objects. And what they did in this paper, they try kind of to create this joint statistics between signals and references. okay? And they create this experiment where they basically define these Bayesian, or this is Markov relations between references and signals. This is the Markov matrix, or the joint probability matrix. It's not really Markov here. Sorry, I mean, I'm kind of misusing here the terms. You have this joint, the probability of reference J. All these references J with this probability will be represented by signal Si. And you can have also the inverse relations. So you can think about this, that the signals are generated by the speaker, and the listener tries to decode the references from the signals. And this is usually modeled as an information between signal and references. So what the listener does, okay, in some sense, he tries to reduce his uncertainty about the references. I'm using the second equation here. These are the definitions of information. And again, sorry for jumping into the math here, but it just helps me to, to structure the argument. So information basically means you have some uncertainty about an outcome, and it's reduced by conditioning this on a signal. So this is really the measure of information. Before we had past and the future, but here it just signals and references. So what the listener does, he has some uncertainty about, what you're talking about. And then by listening to what you're talking about, it reduces the uncertainty about the meaning of your words. And this is the measure of the information. You can also present this in a different way, which is symmetric. So this is kind of the graphical representation. Now, what this paper tried to do is claim that you have this trade-off. So this system basically has two considerations, and the system is the listener and the speaker, and you kind of try to optimize the relations between them, or the effort that each one has. So one is this information that the signal carries, okay, or how hard the listener has to work to understand what you're talking about from the symbols. And the other one is the entropy of the signals, okay, which is the complexity of the language itself, of the signals, that this is the cost for the speaker, right? So if you are the composer here, and you are dealing with choosing messages, the higher the entropy, the more complex is your language. And of course, it can be as complex as your references, but then it will be very hard for the listener to so if the language is very, very specific, the listener will really understand everything you talk about, but you will have a lot of effort, and that will be easy for him. The other way around is you speak something which is doesn't make many sense. It's easy for you, and the listener will have a lot of difficulty. So they kind of try to play around with these weights. I mean, who is paying more price, the speaker or the listener? And the interesting result, even if that whole setting is a little confusing, is this, okay? This is basically the relations between the effort of the listener and the effort of the speaker have to pay. And they show that this is the information that this is the information about the references that the language has, or the effort of the listener, and this is the overall size of the vocabulary. And they show, or the average size of the vocabulary considering the probabilities of the words. And what they show is that for where lambda is very small, okay, which in our case, very small lambda means that basically for small lambdas, let me see, this is close to 1, this is close to 0. So what we try is to minimize the entropy of the language. The language is actually very simple, okay? So very simple languages that have very little entropy, actually do not communicate anything, okay? There is no communication going. Maybe you slightly generate more and more complicated languages. So the whole process was that they were trying to find, they would search for this matrix. They would basically search over the space of possible relations between the signals and the references to find the optimal language, okay? Or the distribution of symbols and the references. So when the language is very simple, actually there's very little conveyed about the real world, okay? When the language is very complex, means it actually ideally describes the word, so you get here. You have perfect communication. And when they mean by animal communication, artificial languages, these are very precise languages. You have symbols that ideally map to objects. And according to their claim, the human language is really at this transition. There is this what they call phase transition. There is something that is kind of optimal balance between the effort of the listener and the effort of the listener and the effort of the speaker, that this is where natural languages reside. This is kind of same scale, same experiment, just giving this average size of vocabulary, which just a different measure of how complex the language is. And here they show the different distributions for different lambdas, and they show that for simple languages you have these kind of behaviors of what should be Zipf. For different higher lambda, which is around 1.41 in this experiment, you get this ideal Zipf behavior. And if you go 0.5 and higher, you get very tilted behaviors. You have a lot of messages, pretty much with equal distributions. You have a lot of, the preferential attachment has a lot of equal clusters, and then it suddenly drops. So what they claim is, because of this kind of empirical evidence, they claim that the natural communication is in some sense this ideal balance between the effort of the listener and the effort of the speaker, okay? So kind of with a little bit freedom of interpretation, I wanted to show some musical examples, and this is a sonata by composer, Michael Edward Edgerton. Now, what he does, I mean, he and it's not exactly clear from his description, frankly, but he uses a slightly different model, which is growing networks. So there are other very much related algorithms to this preferential attachment that grow graphs which have this scale-free behavior. And then you can also try to measure the amount of nodes attached to other nodes. So it's very much like that cluster figure that we saw before. And this is what he wrote about this piece. In part, this first sonata is influenced by a line of work known as scale-free networks. Briefly, what this suggests is that networks are everywhere, from biological to ecosystems, even to the internet. This is not yet well understood, but research is beginning to provide answers. It seems that many networks are dominated by a relatively small number of important nodes or hubs that are connected to many other sites. While hubs have only a few links, others have an enormous amount of links. And it is this sense in which they're scale-free. Further, no node is typical of the others. So I kind of want to play maybe an excerpt from this sonata. And I mean, it's not a machine learning approach. It's totally synthetic system. So it doesn't try to imitate a specific style, but it generates this dynamics of scale free. So let's play this. Okay, I mean, I'll pause it here just because you I want to move on a little bit, and I will post also the slides, so whoever is interested to check this out. Um, and Janet, I was asking about the graph of the human language and animal communications, artificial languages. What does the animal communication refer to in this context? Yeah, so it's a great question. So the idea of this type of behavior, okay, where you have basically, and this is for the high lambdas, they're kind of in this regime, okay, animal artificial languages, is that there is a very high correlation or very strict link between the symbol and the reference. So what I think he means by animal communications, and what also others speak about, the artificial languages or also technical texts like manuals that exhibit this type of behavior, is that the vocabulary is much scarcer. It's much more limited, and it's much more precisely defined. So in animal communication, this would be all kinds of animal calls. So they would have very specific meanings. They will be less ambiguous. So if you have a call for danger, or you have some call for courtship, or a call for something else, for food, or you have smaller vocabulary, and it's much well defined. Now why it's smaller? Just because it's going to be very hard to have such a complex language if your environment is very complex, or if you need to communicate a lot of nuances about the environment and you want to do this in a very precise way, it's going to be very hard. So in that sense, animal communications are much more limited, but they're like specific calls. And this is why artificial languages, in some sense, are also kind of, the idea here is that they're limited in the sense that you define much more limited and less ambiguous vocabulary, and then whatever you say, it refers to something very specific. So this is the meaning of the artificial or the animal communications here. So this is kind of my summary slide. And as I said, this is kind of a different approach. It does not relate directly to the ideas of free energy, unless there is a way kind of to combine them. This is sort of an open question, an active area of research, because the process that so far was offered to explain these dynamics was more of that kind of preferential attachment or creation of context, and it was less evident how this can be explained in the context of homeostasis or homeokinesis, right? It's not just existing in the environment, it's also kind of always introducing novelty. And I think here is kind of an interesting question, because one of the assumptions in the previous models is that there's always something new introduced, right? And we had the question, why do we want to innovate? Why do we want to introduce always new elements? And then the competition between novelty and existing structures, maybe over time, shows these behaviors. But as we have seen, or at least was suggested in the first video, the Vsauce, was that even an individual book, but it has to be large enough, and this exhibit this behavior, or individual musical pieces. So there is something about the fact that how things aggregate and how they build themselves, and that could be maybe just that one instance, that one specific piece already has some kind of a different dynamics that the free energy model not really explains. So trying kind of to summarize, and just maybe following up on Janet's response, bird songs, whale songs. I don't know enough. I haven't explored Zifs laws for these languages. So when this article actually said animal languages, that was my interpretation. It's interesting that people do explore complexities of bird songs. I did mention this before, and there is this idea that birdsongs actually evolve in complexity. But I'm not sure how the function of, let's say, birdsongs, which could be very intricate, right, and have grow very big vocabulary, how it relates to specific functions. And this is a great comment, and actually a great question that would be interesting to explore, really. One set of questions to consider from this exposition is, first of all, it seems that some optimal communication requires ambiguity. Okay, so there is this partial relations of symbols to reference. Okay, which seems to be in the essence of this more natural communication, is that you don't perfectly describe your references, and the references are not immediately determined by the symbols that refer to them. Now, the references do not have to have that have no clear semantics. Okay, and this is kind of my addition here that tries kind of to relate this to the free energy and the idea of latent states. The fact is, yes, I mean, communication could be something that does not necessarily have to have references as enumerated set of objects. Maybe these are kind of latent mental states, maybe some kind of thinking through other minds. But the fact is that context could emerge, and this context could be represented as some kind of a more condensed way or more abstract way, and it does carry meaning, even if this meaning is not clear denotational semantics. So maybe this is where some relations between the two theories can appear. Now, in music, context is determined by hierarchy of intermingled patterns occurring at different times. So this is kind of a suggestion also from the previous papers. And the idea that scale-free behavior of connection between these intermediate representations tend to produce these fractal-like or scale-free hierarchical structures. So maybe this basically emerges just because of the process of telling stories or things that grow through these processes. And now, at least in terms of music, this kind of growth or this structure captures both long-term relations of musical form and short-term relations of the surface, of the musical surface patterns. So again, this is a missing link in some sense between the ability to learn from examples and the ability actually to create a story from learning surface patterns. And I will leave this kind of with the last open question: is in some sense composition, is equal to growing like a context graph, because in composition, at least, the idea that you create a premise, you create some first couple of statements, and then you keep developing them. And by developing them, you basically grow the context of few elements, while you always introduce additional elements. I don't know if this could be considered, a very kind of high level definition of what composing means. But definitely we didn't really explain what composition or how to create a musical form based on the free energy so far. So I felt that we need to address this question if we want to kind of try to think about if there is some kind of a natural mechanism of creating narrative structures. Of course, there are other explanations, and you can say that musical forms and languages are all, in some sense, are faculties that are already pre-wired, or that these types of things emerge because of some historical patterns, or that we learn this based on some other social criteria. But just as a mechanism, just as a dynamical mathematical mechanism, I wanted kind of to present this approach, and also maybe ask you what you think about composition in that context. So I'll stop the presentation now and just turn to some questions.